let's look a bit at dynamics of uniform circular motion. So let's see what each of these terms means. So dynamics has to do with forces that cause a certain motion. We'll get back to uniform. The type of motion that we have is circular motion. So we have an object going around the circular path with a uniform speed. So we're going to have this object go around the circular path at a constant speed. So let's think of a little wind-up car. Let's say that we have this little car and we wind it up. What will it do? Well, it will go in a straight line with a constant speed. Now, if we want to make it go on a circular path, what we have to do is bump the car so that it will go around the circular path. So if this is the view from above of the car, here is the velocity v. In order to make it go on a circular path, we have to give it a little push this way. Then what happens is that the car will turn a little bit like this, keeping a constant speed because the speed is perpendicular to the push that we're giving the car. So here is another push because we want this to go on a circular path. The car will turn even more, keeping the velocity, the speed constant. We'll give it another push. So all of these pushes will make the car go on a circular path. But the direction of this push is always towards the inside of the circular path. So force, push, towards the center of the circular path. So we'll say that the object will acquire an acceleration that we call centripetal acceleration. Centripetal means center seeking. Center seeking. This centripetal acceleration has the form v squared over r. So if we look back at the speed, I said that the speed was constant, but the direction is constantly changing. So the speed here is to the right, here it's at an angle, here is at a larger angle with respect to the x-axis. So whereas the speed stays constant, the direction is changing, meaning that the overall velocity is changing. Changing velocity means that there is an acceleration. So if we're looking at a circular path, we have uniform motion because we're keeping the speed constant. So all of these arrows should have the same magnitude, but the direction is constantly changing. So as a result, we get a centripetal acceleration that points towards the center of the circle. And the direction of this centripetal acceleration keeps changing, so we won't look at every single point along the circular path, but we'll pick a few special ones. So let's say that we have a roller coaster and we have a car up here, and we want to know how fast that car can go before it falls off the track, before it shoots out and falls off the track. So we'll draw the forces that act on the car, and of course there will be the weight, and since it's in contact with the track, there will be a normal force. And those are the only two forces that act here. Now, we are going to always define the positive direction in the direction of the acceleration. So the sum of these two forces of weight and normal force will cause the car to go around the circular path. So we will have a centripetal acceleration down, and that means that we'll pick our positive direction of motion down as well. So now when we write our sum of the forces equals mass times acceleration, the force that points down is the weight, and the other force is the normal force. So sum of the forces is weight minus normal force is equal to the mass times the centripetal acceleration. Now, we have come into the habit of calling this the centripetal force. But it's not really a force because it's not something we draw on a free body diagram. It is the net force that acts on an object, making that object go around on a circular path. So it's the mass times the net acceleration that we'll call the centripetal force. All right, so now my question was, how fast can this car go before it flies off the track, before it loses contact with the track? So losing contact means that there is no longer a contact force. So the normal force disappears. Losing contact. So what that means is that we're left with weight equals mass times centripetal acceleration, and the centripetal acceleration is v squared over the radius of the circular path. So that means that v would be weight times r divided by m and square root of that. So I can write the weight as mg and cancel out the m, so I'm left with v is square root of r g. So the velocity that the car should not go faster than is this square root of rg. So v is square root rg is the limiting velocity. Let's look at another example. So let's say that we have, let's move this down. Let's say that we have a mass that we are rotating about this point. So in a vertical circle, so here is the mass going around a circular path like this. And we want to look at the forces that act on this mass when it's at the top of the trajectory. So the mass has weight, but it is also connected to a string. So that means that there will be a tension force in here as well. Now both the weight and the tension force act down. Furthermore, the centripetal acceleration is also down. So that means that we will pick the positive direction to be down. That's a lot of arrows going down. So when I write sum of the forces is equal to mass times acceleration, the forces are tension in the positive direction plus weight, and that's equal to mass times v squared over r. So tension plus weight is mv squared over r. Just like in the problem before, there is a question that can be asked, a trick question, and that is, how fast should this mass rotate so that the string does not become slack? So how fast should the mass rotate So the string wouldn't become slack. So becoming slack means that the tension would go to 0. So again, when we set tension equal to 0, we're left with the weight is mv squared over r, and just like in the above problem, you end up with the velocity is square root rg. Now this is not to say that it's the exact same problem as the one above. It is similar but not quite exactly the same. Another thing to note here is that as the object rotates on a vertical path, vertical circular path, the string has a different tension at the top and at the bottom. So if I were to look at the string, at the mass when it is at the bottom of the path, so here it is, the forces that act on it are the weight, and now tension is up. So sum of the forces equals mv squared over r would translate to tension minus weight equals mv squared over r, because now tension is in the positive direction since the acceleration is up towards the center of the circle. So tension is a positive force and the weight is the negative force in this particular equation. So if I were to solve for the tension force in this equation, I would have mv squared over r plus the weight. And in the previous example, if we're looking back here, tension plus weight is mv squared over r, then I can solve for tension and get mv squared over r minus w. So those two equations, this and that, are different. Tensions are going to be different at the top and at the bottom of the trajectory.